this work I'll talk, there's many co-authors listed here, and then in the end I'll give also more complete references. I kind of put this talk in a context that I'm interested in all parts of Bayesian workflow. And then this figure is from our recent archived paper on Bayesian workflow. And then with today, I then talk more about the kind of the parts that are related and or useful in here in convergence diagnostics, cross-validation, and in some other parts, but kind of that I'm interested in all parts of this, but this talk is now focused on this. So I will briefly remind you about Monte Carlo estimates, important sampling, and central limit theorem, which is used to justify these often. And then I go to concrete example of Leeuwenhoek cross-validation, which was the kind of the reason I started to think more about these pre-asymptotic behavior and diagnostics for that. And then that's the main part. And then 3 other examples of using it in validating and improving the end result of variational inference, diagnosing the stochastic optimization, and then as last reminding again that it can be just used plain Monte Carlo estimates also. So in Monte Carlo and markups in Monte Carlo, we get some draws, and theta are, for example, parameters, and p theta could be then like posterior distribution for these parameters, and we get draws from that distribution. We may have some function h, and then we want to know expectations of that function, the h theta, integrated over that distribution p, and we can do that with just empirical average. And so this h could be just like identity, and we get like posterior mean. It could be squaring, which is needed for variance, or indicator function, so we get probabilities and so on, which are needed in like Bayesian inference. And then this is consistent, unbiased in case of MCMC asymptotically. And then this is often justified with central limit theorem, which then, assuming finite variance of this expectation estimate goes down with respect to then, so divided by the sample size. Important sampling. Instead of getting the draws from the target distribution directly, we instead have some other way it's easier to get, and we still can compute these expectations, estimate them. We just need to now weight them, and these weights are just using the ratio of the target and the proposal distribution. Again, consistent, unbiased, and if it's the case that 1 or 2 of these distributions that we have only unnormalized, so we don't know the normalization constants, we can do self-normalized, so we just divide by the sum of these weights. Consistent and bias decreases with the sample size. And these are kind of these consistency, unbiasedness, or small bias. Central limit theorem have been used to justify that, okay, now we are using this. And in the important sampling, if these, that kind of the function times the weights and the weights, if these distributions are finite variance, then the estimate has finite variance, which implies, again, central limit theorem. And then now, instead of directly just dividing by S, variance in the weights decreases, the performance, and then there's this effective sample size estimate. In this case, I show you just this approximation that ignores that function age. There are also age-specific versions. And so we get the effective sample size just by 1 per sum of squared normalized weights. So the weights sum to 1 then. And this is actually then related to just to the variance of these normalized weights. And then this SF can be smaller than this total sample size S. And again, kind of the useful and useful thing. There's also additional useful aspect is that if it happens that there would be infinite variance, we still would have a finite mean, and then with the infinite variance, this estimate the error distribution would converge to generalized. So the generalized central limit theorem would hold, and we would converge towards this stable distribution. It's useful to know later in this talk. So often it's kind of given granted that we have finite variance and central limit theorem just holds. Sometimes we can do it so that we can guarantee finite variance by constructions. For example, in case of importance sampling, if we choose Q so that the weights are bounded, then we know that we have also finite variance and central limit theorem holds. But it's not generally trivial. And I will also show that this pre-asymptotic behavior can be then quite different than what central limit theorem says. But okay, now I'll go to this example which started my path to thinking about this diagnostics. Leave and out cross-validation. Yes, true data generating mechanism is linear function. Y depends on X linearly, plus there's then just normally distributed variation around that mean. There's one data realization from that process. We can fit linear model there. There's a posterior mean. And then because it's a finite realization, we have uncertainty, which can be then represented with posterior draws shown here. We can compute predictive distribution. And then here we are just, this is the predictive distribution that if we would know the parameters, and since we don't know parameters, this reflects the uncertainty, and then we integrate over that uncertainty into parameters to get the predictive distribution. And then we would like to know how good these predictive distributions are for new data. But if we don't have a luxury of waiting new data and testing, we can instead then choose observation and remove that, and then fit the model again. So and now the green line is then showing the what would be the fit without that observation. And we can also then compute the leave and out predictive distribution. So now instead of using that full data posterior, we are using this leave and out posterior, where these denote that we have left out the 18th observation. And you can see then that this predictive distribution is different. But now we can also then use that left out observation as new, kind of the proxy for new future data. And the importance why we need to do this kind of cross-validation is that if we would evaluate the predictive performance just by evaluating like the predictive density given that 18th observation, but conditioning on all the data, we get some predictive density. But usually these leave-one-out predictive densities are then lower because it's more difficult to predict something that you did not see. And then we can make a summary so that we repeat this process for all, in this case, 20 observations, compute these predictive densities. And it's actually useful to take a logarithm and sum or average of these values. And this would be the summary of how good we think that this is for predicting future data. And this is almost unbiased estimate of log posterior predictive density for new data. And then this can be used in model comparison, model selection, and of course we can compute other things using other utilities and cost functions than just log score. And then again, reminder, if we would not use these leave-one-out predictive distributions, we would get higher value, like here the difference is about 3, which happens to be close to this number of parameters in the model, intercept, slope, and the standard deviation for the residual parameters, which reflects that given these 3 parameters, we were kind of fitting to the specific data, and then this is but then this is biased estimate for the performance for the future, and then this is almost unbiased. And then there are these papers discussing specifically more about this leave-one-out cross-validation. But now the issue is that we would need to compute here, in this case, 20 times these leave-one-out posterior. If we did use MCMC for the full posterior, and then we would do 20 times again this MCMC for more complex models that can take considerable amount of time. So now if we already did sample from the full posterior and we already have these draws, we can use this as a proposal distribution, and this is the target distribution, and or in this case we have them as many as we have number of observation, and then we can use impedance sampling, impedance ratios. So we have the leave-one-out posterior divided by the full posterior, and if you think about in the cases where we have factorizing likelihood, this full posterior has one likelihood term more than this one, and then if we ignore normalization terms, then this impedance ratio is proportional to just 1 per 1 likelihood term. And then the S is now indexing this these draws from the full posterior. And then we can normalize these because we don't know now this normalization constant, and use self-normalized impedance sampling. Here's again the same data on the full posterior, and then for the full posterior we would have just the empirical average to get this predictive distribution. But now if we choose that one observation and leave it out, now notice the difference. I have exactly the same lines in this figure and the previous figure. I only changed that the alpha channel has been chosen based on these weights. So if the weights is close to 0, alpha channel is 0 and you can't see it. And if alpha, then the weight is larger, then the alpha channel is closer to 1. And so this is the only difference. I only weighted the draws, and these draws are now then better reflection of the leave-one-out posterior. Of course, if the leave-one-out posterior would be very, very different, and we would not have that kind of draws at all, we would fail, and we'll kind of these diagnostics I talk about is related to this. And so now we can then compute this leave one out predictive density for the left out data. So predictive density, we would know the parameter values, and then these are draws from the full posterior, and then we just weight them using the normalized weights. So easy. But then the question is, how reliable now this estimate is? Is the variance finite? Is the central limit theorem kicking in there? There's no general analytic solution. For specifically for the leave one out cross validation, there are special results for normal linear models and one specific other type of model, but not, there's no general solution. And it's also usual that the target tends to have thicker tails than the proposal, because when we leave out one observation, there's more uncertainty, and then it's also likely that these weights are not bounded. So what we can do is we can look empirically the distribution of the weights. I'm first showing now just 400 draws so that it's a bit easier to see these largest weights in this histogram here. And so even the largest weight, it's not close to 1. So these are now these normalized weights. So this should have a tilde there. And also this would be what would be the size of the weights if they would be all equal. And we have a lot of weights around there. So it seems like that this is not that bad case. This is with 4,000 draws. And now it's a bit difficult to see, but there's the largest weight, and now I can't even see. If I have this really big, I can see that there are also somewhere around there other weights. I mentioned the effective sample size estimate, and yes, so here we had total sample size like 4,000, and the effective sample size based on these variance approximations is around 400. 400 it is not bad, 10% its efficiency not that good. But then the question is that, is the variance finite? Can we trust this effective sample size estimate? And of course, with any finite sample size, we will get also the variance estimates are also finite. So directly looking at the variance estimate doesn't tell whether the variance is finite. So what we can then do is use something else to estimate whether the variance is finite. So what we do is that we fit generalized Pareto distribution to the largest ratios. So we ignore the bulk and we choose some cut point. And then from that cut point, the generalized Pareto distribution is such that it has some cut point there, and then it's decreasing. It has some scale parameter, and then it has the shape parameter that affects then how thick the tail is. And we fit it to only to the large ratios. And there's a theory that's saying that if we choose this cut point far enough in the tail, then there's a very large set of distributions that this tail part is well approximated with this Pareto distribution. And the nice thing about the Pareto distribution is that it has this scale parameter and shape parameter. And the shape parameter k is such that now floor of 1 per k tells the number of finite moments. And then we have finite variance and central limit theorem holds.
Can I ask a question?
Yes.
So this sort of extreme value theory, usually it's for ID observations, but if you run an MCMC chain, then you have a Markov chain, you don't have ID observations. So is it taken into account?
Yeah, so usually this extreme value theory, so for the dependent data, there would be the issue if we would be asking a question that what is the probability that we would observe weight which is larger than something. But just for estimating what is that shape parameter, that's not the issue. So it's just that in a way that we would need to take the dependency only into account if we would say something about the like how likely it is that we would see even extreme weights. Okay.
Thank you.
But now, so we don't know. So we are not stating anything about the kind of how likely we would see more extreme weights. We just want to know the shape parameter, and then if this shape parameter would be less than half, variance is finite, central limit theorem holds. If k is less than 1, generalized central limit theorem holds, and so on. In this case, we estimate the k hat to be 0.52. So it would say that, okay, now central limit theorem doesn't hold, but we will soon see that the kind of this, whether k is less than half or above half, there's no, in a behavior, there's no sharp threshold. Before going to this diagnostic part, I'll add also, because these diagnostic examples, they show results based on specifically on Pareto smoothed importance sampling. So in addition of using this Pareto distribution for diagnostics, we can also use it to replace the largest weights with ordered statistics of the fitted Pareto distribution. And this is equivalent to using model to filter noise out of weights. Here's an illustration. Each blue line is from one repetition of simulation. In one simulation, we draw 10,000 draws from some proposal distribution, some specific proposal distribution, and there's specific target distribution. We rank the weights, so we sort the weights to increasing order, and you can see, so this is the largest, 10th largest, 100th largest weight. And then in each simulation, you can see that there's a lot of variation in the largest weight. There's an approach also truncated importance sampling, which just truncates the largest weights. And of course, it then reduces variability. But now you can see that instead of having these jumpy lines, these are smooth lines because we replaced these kind of observed ratios with smoothed ratios based on fitting this Pareto distribution. And it then reduces the variability compared to plain importance sampling and reduces bias compared to the truncated importance sampling. And here's an example then, again, 100 simulations, but now with the increasing S, estimating the normalization constant. And in this case, we are in the region where the K is like close to 0.5, and then regular importance sampling has these jumps, and so it is unreliable, even if we get more observations that it can sometimes jump a lot. Truncated importance sampling doesn't have that issue, but you can see here it's getting below the true value, so there's bias, and then Pareto smoothed importance sampling has both reduced variability and bias. We also prove in the paper, thanks to Dan Simpson, that this Pareto smoothed importance sampling estimate is asymptotically consistent and has finite variance under some mild but complex conditions. Cool result also is that we can connect this K to minimum sample size that gives some tail guarantees for the error in self-normalized importance sampling. And simple equation which look like this. So let's say that we have the case where k is small and 0 corresponds to having the distribution of weights being exponential, and less than 0 would correspond to having bounded weights. In that case, let's say we have 100 draws. If we would have independent draws directly from the target distribution, 100 draws is often sufficient for like posterior mean expectation. And then we can, instead, if we now would have a proposal distribution such that k is estimated to be 0.7, for the same accuracy, we would need more than 100,000 draws. You can see that there's no sharp change at k 0.5. So that way, previously there was also suggestion to estimate, like to make a hypothesis testing whether the variance is finite or not, and then just abandon the hope if the hypothesis test would say that variance is infinite. Instead, we just use the k continuously because there's still hope here. Although then, after about 0.7, the kind of the required sample size it start to be that big that it's not sensible. And like in this leave-on-out cross-validation, it would be better than to use something else than simple importance sampling, maybe even just refit them with MCMC. That was the theoretical result, and here's an empirical comparison to the theory. Showing root mean square error, knowing the truth. And let's focus first on just on the black lines, which are then root mean square error, given different proposal distributions. And the values here tell how good these proposal distributions are, because these are the k-hat values. So from quite small and eventually around 0.7 and 0.9. And we can see that, so the error goes down when we get more draws. But this is also reflecting that, like here, we have these 100 draws and we have the kind of good proposal distribution. Error is somewhere around here. And then if we draw parallel on the horizontal line, we can see that if k would be around 0.7, it would also empirically match that we need more than 100,000 draws to get the same accuracy. The red dashed lines are Monte Carlo standard error estimates based on this, the effective sample size estimate I showed you before. And they match well. They match quite closely, even here. This is close already to 0.7. And so this red dashed line and this black line are the pair, and they are close. But then we can see that when the k-hat grows larger, then this error estimate starts to be also too optimistic. But it's not that bad, because we know based on the k-hat that we can't trust them anymore. What is also interesting, you can see that the angle of this, so this angle of this is actually now corresponds to that the speed of convergence is this var theta divided by s. But then when the k-hat is clearly larger than 0.5, the angle is different. And we can summarize this so that here, this is the convergence rate so that usually in the good case, so we would have this s to -1, but now we get worse convergence rates when k is larger. And for example, around 0.7, we have the convergence rate is then again only then the var theta s to 0.6. There's a kind of smooth curve, which is partially, of course, because of the kind of the limited simulations and limited the length of the simulations. And then, but it's also related that there's no really super smooth transition. Otherwise, there's like starting from 0.5, if we draw a line, this dashed line, the behavior goes quite close there. Here, the blue line is for the 0th moment, so the normalization term, first moment, mean, second moment. So using also then these function-specific estimates, and they have the kind of the similar behavior. So when we get the k, we can say then, okay, what would be the minimum sample size required? And then we could also say that how much we could expect that the variance decreases if you get more draws. So we do this empirical Pareto K using the largest ratios. We have ad hoc rule selecting how many largest ratios to use for estimating K, and then this rule is also such that it fulfills then the asymptotic properties that we always go further in the tail, but at the same time increasing the number of draws so that the estimate gets more accurate. Smallest amount in the experiment has been like 20 largest ratios from 100 ratios, and useful, but of course has a lot of variation. We use empirical profile-based estimate by Chang and Stephens. Excellent accuracy compared to MCMC. So seems that there's no need to look for more accurate estimates for this. And see the paper for more details. Then the usual question has been from the reviewers that why bother with Pareto smoothing, improving the estimate in cases where K is larger, or like where the variance is infinite, and why don't you just select the proposal so that ratios are bounded? Yes, that would be nice, but it's not always trivial, as in the importance sampling, leave one out. But even bigger problem is that high dimensional spaces are not intuitive and they are really scary. And so here's an example. By construction, we have bounded ratios, finite variance. So the target distribution is normal distribution. And then the proposal distribution is a student T. It has thicker tails than normal. And so the imponent ratios are bounded always. We use 100,000 draws a lot, and then just vary number of dimensions. Here's the effective sample size. So in low dimensions, we get quite good efficiency, close to 100% efficiency, but then the effective sample size starts to drop, and it goes eventually to 0. So why is that? Also, if we look at the convergence rate, that how much additional draws reduce the error, the convergence rate drop. So even if by constructions, we have bounded ratios, finite variance, asymptotically central limit theorem holds, pre-asymptotically, the practical convergence rate is less and eventually goes to even 0. The good thing is that k-hat can diagnose this pre-asymptotic behavior. So as we have bounded ratios, the true k is actually less than 0, and in the beginning, in low dimensions, k-hat is also less than 0. But then it goes above 0, then it goes above 0.5, above 0.7, and around there, the effective sample size starts to be 0 as we did show that around 0.7 we would need more than 100,000 rows. And then it keeps growing, and then convergence rate crashes. So why is this happening like this? Why don't we see the asymptotic central limit theorem behavior? So I'm now using blue line for the normal distribution, and then this proposal d-distribution with red line. And this is a marginal density, showing just a distance from the mode. So 500-dimensional distribution, and then we draw 100,000 rows. And then when we compute how far these draws are from the mode, we get this kind of distribution for these 100,000 rows. And this is for the proposal, and this is for the target. So from these 100,000 draws, most of them are closer to the mode than what would be the draws from the true distribution. And now, if we add here, what is the importance ratio? We can see that the importance ratio is bounded. But look at the scale of the y-axis. The largest weight is around that size. And also, before we would see that these ratios are bounded, we would need to see some draws around here. And looking at this distribution, it's quite unlikely that we would get draws around here. In this specific case, it's possible to compute that the number of draws we need to get something here, it's much, much larger than the number of atoms in the universe. So there's no hope that we would reach asymptotic regime. And thus, it is very useful that we can diagnose this pre-asymptotic behavior. If I now scale this so that I showed it only up to 10 to 30, how the importance ratio behaves here, it's just almost like a wall. So in the region where we are getting draws with reasonable sample sizes, it looks like it's indistinguishable from infinite variance case. And then we can see this with this empirical Pareto K. It is also possible, like in this case, if it would make it less extreme, it would be possible that like maybe after 10,000, it looks like the variance could be infinite unless say after like 1 million draws, we might start to finally see that it's actually bounded. It is possible to see this also then when you get more, the Pareto K eventually starts to also recognize that it could be bounded. So it's not saying kind of what would be if we would keep infinitely sampling. It just says that, okay, at this moment, it looks like your performance really bad, and it looks like you are not getting much better if you get more draws. Okay, so that was the main part about the diagnostic, and then I'll discuss these few applications. So what is the end result of variational inference, stochastic optimization, for example, variational inference, and just plain Monte Carlo estimate? So in variational inference, it's often like normal distribution is used, fitted to some unknown posterior distribution, and then we can use that as a proposal distribution in sampling. And then that means that we can use it both for diagnostic and improving. In this case, we would like to use this. So this is this order different associated variational inference, which is kind of black box variational inference, and compare it to MCMC. Here we used U-turn sampling time was then this, and you can see that we can run ADVI in less time, but also that if we run it too short time, the stochastic optimization hasn't converged yet, and then this normal approximation is bad, but we can use the k-hat to recognize that, okay, now the optimization result is actually good. And we can also see here that in addition of diagnosing that it's good result, instead of using just that normal approximation, using that normal as a proposal distribution, we can get lower root mean square error with this. And then again, Pareto smoothing helps here a little bit. And there's the reference. Then this ADVI and many other these variational inference algorithms use stochastic optimization. And often in these papers, it's been said that, okay, we reduce the step size, and if it fulfills Robbins-Monroe condition, it will eventually converge, and then they've used just the last iterate. But actually then this optimization is stopped much earlier, and then the last iterate can be very, very kind of noisy choice in that stochastic optimization. And then there's this Polyak-Rupert averaging, also known as iterate averaging, which instead use many of the iterations from the end. And here's an illustration again how we can use this k-hat to show that especially when the number of dimensions increase, this optimization problem gets harder. Using just the last iterate gets noisier. K-hat shows that the approximation is worse, while with iterate averaging, we stay near 0.7, so much more stable. Then, in addition of looking at this stochastic optimization part, is also that what divergence to use. Usually this exclusive KL is known to often to underestimate the posterior uncertainty, and so people have been proposing other divergences which are more mass covering, such as inclusive KL and chi-squared and so on. And many of these common divergences can be presented as expectations of the density ratio. So this is the same density ratio as before, and then there's just some function, empirical average. So just the same thing we've been doing. And here are what are these different Fs for different these divergences, objectives. So exclusive KL, log W, and we can also know there's an earlier paper on theory saying how many moments of for the W we need. And so here delta, which just needs to be larger than 0. And then, for example, inclusive KL instead requires 2 finite moments and then delta, which needs to be larger than 0. So you can now guess that then it's more difficult to estimate inclusive KL and then exclusive KL, given these Monte Carlo estimates. And again, high dimensional spaces. So exclusive KL, it's known to often underestimate. And here also, again, when we increase the dimensions 2, 5, 10, 50, it is, the red one is the approximation, it is underestimating. Inclusive KL here in low dimensions, it is overestimating, and it's giving bounded ratios, which is nice. But this overestimation in high dimensions is actually bad. Now these typical sets are not overlapping anymore, and it's unlikely that from this inclusive KL proposal distribution, which is overestimating the scale, we would get draws around here. And if you don't get draws from there, we will get bad behavior of these Monte Carlo estimates. And here, Pareto K shown if we optimize exclusive KL, so that which is like to underestimate, and also then how well we are actually being able to estimate these certain terms. So this was needed for exclusive KL, and this was needed for inclusive KL, and this was needed for normalization constant. So it's easy to estimate this exclusive KL, and also the normalization constant, it goes above 0.7, so not that good. But if we compare that, if we are optimizing inclusive KL, it's good in low dimensions, but eventually it will go much, much higher. So it's much worse, both for the normalization factor and that divergence measure itself. And just reminding that from the Pareto K, we could see also that how many draws we would need. And in this stochastic optimization, that in each step of stochastic optimization, we would be using these many draws, it's infeasible. And then also, what is the effect then that these Monte Carlo estimates start to fail? The point is that here, so the dashed line is the true exclusive KL. And this continuous line, the dark green, is then what is the estimated. And so we are underestimating also the divergence. And in this pre-asymptotic behavior, they look like biased, just because it's so unlikely that we would ever see these overestimates. And so in the practice, we see this biased behavior, which can explain now these results, that why still this exclusive KL is so much more common than these other divergences, why people have problems of getting other divergences to work reliably, and so on. And so with too small sample size, the divergences can have significant pre-asymptotic bias, which can affect the results. And yeah, again, we may need more draws than the number of atoms in the universe to make these reliable. And there's the paper where there's more results on this. And the final example, so that's just reminding that what I was talking is not just importance sampling and variational inference. It can be used just for plain Monte Carlo. In this paper, Banan et al., we did study this leave-and-out cross-validation, but we wanted to compare importance sampling, leave-and-out cross-validation also to the case where we actually then use MCMC to sample from these. And then these draws are actually directly from the target distribution. But we did get seemingly biased results because so this distribution here was normal distribution, yi, and then given some predictive mu, and then sigma. And now then, when we have these draws of these parameters, if we go far enough in a tail, these densities are very close to 0. And then by just chance, one of these is that much away from 0, so that this distribution of these densities is very, very skewed. And we see the same behavior as we could see with this importance sampling case. And we can just look at it then using the Pareto diagnostic also, just directly how long tail these draws have, and can see that, okay, actually MCMC is also failing to give the exact or the resulting, like with the reasonable amount of draws. Okay, that's it. And here are the papers I've mentioned throughout the talk and the co-authors